the manufacture of microchips from sand is a complex and intriguing process. It begins with the extraction of silica sand, which is subsequently processed into pure silicon, and eventually into the complicated circuits that power contemporary electronics. Here's a 7-point overview of this remarkable journey. Extracting high-purity silicon from sand. The voyage begins with silica sand, which is common in nature and mostly consists of silicon dioxide. Silicon dioxide itself is not conductive. Thus, the initial step entails separating pure silicon from the sand. This is accomplished by heating silica sand and carbon generally in the form of coke or charcoal to extremely high temperatures, usually around 1,800 degrees Celsius, in a boiler. About 99% pure silicon of metallurgical grade is the result of the reaction. This level of purity is not enough, though, for the production of microchips. The silicon is further refined using chemical methods like the Siemens process to produce electronic-grade silicon, which is 99.9999% pure. This procedure involves reacting silicon with chlorine gas to produce silicon tetrachloride. Through a sequence of chemical events, including reduction with hydrogen, this gas is then refined and re-solidified into ultra-pure silicon. Because it guarantees uniform electrical characteristics throughout the material, this ultra-pure silicon serves as the basis for the production of semiconductors. Because even minute levels of contaminants can have a major impact on microchip performance, the purification process is essential. To reach the necessary purity standards, the entire process from sand to electronic-grade silicon involves several heating phases, chemical reactions, and purification procedures. For silicon to function as a semiconductor material in a predictable manner, this degree of purity is necessary. Crystal growth and ingot formation. Once the silicon is purified, it must be transformed into a single crystal structure to ensure uniform electrical properties across the material. This is done using the Czochralski process, where the purified silicon is melted in a quartz crucible at high temperatures. A small seed crystal of silicon is dipped into the molten silicon and slowly rotated and pulled upward. As it cools, it grows into a large cylindrical ingot made entirely of single crystal silicon. These ingots can weigh hundreds of kilograms and measure up to 2 meters in length. The single crystal structure ensures that atoms are arranged in a perfectly ordered lattice, which is critical for predictable electronic behavior. The purified silicon must be transformed into a single crystal structure to ensure uniform electrical properties throughout the material. The Czochralski process involves melting the purified silicon at high temperatures in a quartz crucible. A little silicon seed crystal is dipped into the molten silicon, then slowly spun and pulled upward. As it cools, it forms into a large cylindrical ingot made entirely of single crystal silicon. These ingots can weigh hundreds of kilograms and reach a length of 2 meters. The single crystal structure ensures that the atoms are arranged in a finely ordered lattice for predictable electrical activity. Wafer slicing and polishing. After the ingot is formed, it is cut into thin wafers with diamond-coated saws or wire saws to achieve very precise thicknesses, usually less than 1 millimeter thick. Each wafer is used as the substrate for creating microchips, but cutting leaves rough surfaces that are not suitable for advanced semiconductor fabrication. To solve this, wafers are subjected to chemical-mechanical polishing, which uses abrasive slurries and polishing pads to create an ultra-smooth surface free of scratches or imperfections, as well as chemical treatments to remove microscopic contaminants and guarantee that the surface of the wafer has uniform properties throughout its entire area. The polishing process is done in stages, beginning with coarse abrasives to remove major imperfections and moving on to finer abrasives for a mirror-like finish. Because even minute flaws can have an impact on the photolithography process and later stages of material deposition, the ultimate surface quality is crucial. To guarantee a spotless surface for additional processing, the wafers are additionally cleaned with specialist chemicals to get rid of any last contaminants. Photolithography for circuit patterning. One of the most important processes in the production of microchips is photolithography, which establishes the complex designs that make up the circuitry of the chip. Initially, the surface of the wafer is coated with a layer of photoresist, a substance that is sensitive to light. By serving as a stencil, a photomask with the chip's design on it lets ultraviolet light shine through particular regions onto the photoresist. The photoresist in exposed parts is chemically changed by the UV radiation, becoming harder while remaining soft in unexposed portions. After the unexposed photoresist has been removed from the wafer using a developer solution, a precise pattern that matches the chip's design is left on the wafer surface. Transistors and other components can now be precisely defined at the nanometer scale thanks to this step. For the most sophisticated chips, modern photolithography employs sophisticated techniques like extreme ultraviolet lithography, which requires light with wavelengths as low as 13.5 nanometers to achieve finer resolutions. To guarantee that it faithfully captures the chip's design, the photomask itself is made using advanced procedures. To guarantee that the pattern is precisely copied onto the wafer, the entire process is highly automated and controlled. Pressure and gas composition is necessary. The intricate architecture seen in contemporary microchips are constructed by repetitive etching and depositing, where each layer must be precisely aligned and patterned to guarantee proper chip operation. Doping and ion implantation. Certain parts of the silicon wafer need to be doped with impurities like phosphorus or boron atoms in order to regulate the flow of current through particular locations of the chip's transistors. Ion implantation is a technique used in this process, in which high-energy ions are propelled at precise angles and energies determined by the photolithographic pattern towards particular wafer locations. By forming p-type positive or n-type negative semiconductor areas, these ions change the electrical characteristics of silicon by embedding themselves into the lattice at precise depths. Transistors, the fundamental components of microchips, can turn on and off efficiently thanks to this procedure. To properly manage the energy and dosage of ions during ion implantation, advanced equipment is needed. The next stage is thermal annealing, which is essential for obtaining the required electrical properties in the microchip since it fixes any damage from the implantation and activates the dopants, making sure they are dispersed uniformly throughout the silicon lattice. Testing, dicing, and packaging. Following the fabrication of every layer on the wafer, it is put through a thorough testing process to make sure every single chip works as intended. Automated systems use tiny needles or lasers to probe each die on the wafer for electrical performance flaws. Automated saws cut or dice the wafer into separate chips called dies after testing verifies functionality. Depending on the intricacy of the design, each die contains millions or billions of transistors. After that, these dies are placed in protective cases composed of ceramics or plastics and include copper or gold metal connectors that enable them to be integrated into electronic devices like computers and phones. Before packaged chips are transported all across the world, final testing makes sure they fulfill quality standards. Encapsulation in a protective material, wire bonding or flip chip bonding to link the die to external pins, and final testing to make sure the packed chip functions as intended are all steps in the packaging process. In order to guarantee consistency and dependability across the billions of microchips manufactured each year, the whole process from wafer creation to packaging is highly automated and monitored. In conclusion, the transformation of sand into billions of microchips is a testament to human innovation and technological prowess. As technology continues to advance, the role of these microchips will remain crucial in shaping the future of electronics and beyond. If you liked our video, please hit the like button and subscribe to our YouTube channel.